This is the lecture for Chapter 5, Acoustic Phonetics. We've been talking about how sounds are produced and how to represent those sounds when we transcribe them. Now we're going to look at sound and how sounds are produced in a very different way. We're going to actually look at more of the scientific form of sound. So what is sound? It's pretty much air molecules in vibration, or the passage of a disturbance through the air or other medium. If you think about dropping a pebble into a pond or a pool, it ripples, and that's kind of what sound waves look like. In creating speech sounds, you have your air supply, which is your lungs. You have your source of sound, which are your vocal folds, and then the source of change in the quality of sound. So that's why people sound different, because their oral cavities and their nasal cavities are different sizes and shapes, and that gives you your own unique vocal quality. Sound waves. As sound propagates through the air in waves, there's high pressure and low pressure. So when you look at a sine wave going up and down, the high pressure is up on the top and the low pressure is down below, and that goes very fast as it moves through the air. The air molecules actually behave kind of like small springs. They're bouncing off of each other as it goes through the air. There's two kinds of sound waves, periodic sounds and aperiodic sounds. The periodic sounds is a pattern that repeats itself at regular intervals. It's a pure sound. Let's say I had a tuning fork and I hit it against the table. That pure sound of a tuning fork is what is a pure sound. And they're regular waves. When you have aperiodic waves, you have no regular repeated patterns. Let's say your television loses reception for some reason and you get that white noise, that is an aperiodic sound. It's kind of random. It's white noise. It also is obstruents in our speech. It's those irregular waves. There are two kinds of periodic waves, sine waves like that tuning fork. There's simple periodic waves, there's like kind of oscillating motion. And then we have complex sound waves like our vowels. We don't have anything obstructing the air flow like when we have consonants. So our vowels are more complex sound waves. They are added to one another. Here is an example of periodic and aperiodic waves. This is actually an example of the word Sam. So S is very white noisy, and it is very aperiodic. You have the vowel, the A, and then you have the which is much more regular. You can see pattern within that. So we have periodic, aperiodic. When we look at amplitude, that's how big the wave is. So when we have a S, if you notice, the amplitude isn't as big as when you have an The amplitude is much bigger. We tend to think of amplitude as it's perceived as loudness. So if I'm talking really soft, your amplitude is much smaller on the wave. But if I'm using my outside recess voice, I'm not going to yell, it is much larger. So loudness is the amplitude that we're looking at. It's the difference of air pressure between the greatest value and the neutral value. That's how it's represented. Frequency, on the other hand, is how often it goes up and down. And a cycle is from the point that let's say, should use an example. So if we say this is our line and it goes up and down and up, that is a whole cycle. Now let's say we have 20 cycles per second. That actually converts into something that we call hertz. And so it's 20 cycles per second. It is 20 hertz. It is actually perceived as pitch. So the lower your voice is, if you go really low, the pitch is much lower. If you talk really high or go way up high or sing really high, the pitch is much higher or bigger. So let's say a really low person's voice would be maybe 100 hertz, where a really high pitch might be much higher, 500 hertz. The frequency is actually measured in the duration of a second, and usually they measure them in milliseconds. So let's say if one cycle is 5 milliseconds, the frequency would be F divided by 1,000, or equals 1,000 divided by 5, or 200 hertz. So think about it. If a frequency is 20 hertz, how big is that going to be? I'll let you think about that and figure that out on your own. The pitches range in a healthy human voice that we can hear from 20 hertz to 20,000 hertz. I now think about that ringtone that older people cannot hear, but teenagers can. That's because our hearing is decreasing as we get older. I think anybody over 30 can't hear that sound. That's a much higher frequency. That would be a higher hertz. If you, the pitch range in speech is usually 60 hertz to 500 hertz. And if you have something like a S, that's going to be a much higher sound, or a F, but if you have a M, that's going to be a lower sound. The typical range of pitches in speech are children are 200 to 500, women are 150 to 300, and men are 80 to 200. And that's all measured in hertz. I'm going to show you a wave, and this is a pretty pure wave. We're going to look at the harmonics and the fundamental frequency. The fundamental frequency is the bottom line, and then the harmonics are multiples of that line. If you notice here, here's the first harmonic, and then they actually count it up, and this is the 10th harmonic. And if you notice, they're multiples of one another, and so they're spaced evenly. If you look at that, it starts down here, but when it says in union, so those fundamental frequencies and those harmonics change as they go along. So F0 determines the pitch that we perceive, and I'm going to use an example of hitting a key on a keyboard or a piano. The fundamental frequency is the one that we hear, the actual note that we hear. And then the harmonics are actually multiples of that, and you can actually, that gives it the richness of sound in a piano note. So harmonics are multiples of the base frequency, F0. So let's say a wave is 50 hertz. Its harmonics are going to be 50, well, that's the fundamental frequency, 100, 150, 200, and so on and so on. Resonance is the actual shape and size of whatever the sound is coming through. So that is your vocal tract, that is your mouth, that is your nose. All of those shape the resonance or the sound quality that we hear. And those also show up on our spectrographs, which is where we're going to learn to use Pratt. Amplification of harmonics also depends on the shape of the vocal tract. Some harmonics are amplified while other harmonics are dampened. It shows the frequency in which harmonics are strongly resonating. Those are what's going to show up. So let's look at a sound wave. This is just a pretend sound wave. But we have, if you notice, 3 bumps on this sound wave. You have a big bump, and then it kind of goes for a little bit, and then another one and another one pretty close together. We actually call these humps formants, and that's what we're going to be looking at when we look at spectrographs. This is formant 1, that peak. Formant 2 is the second peak, and formant 3 is the next peak. Remember, amplitude helps us find those, but it's the intensity of that note or that formant that we hear.